Hi, and welcome to this Tracetronic demonstration. Today we want to show you the ecu.test infotainment capabilities, and for this reason I brought Lukas with me to show you how to analyze this HMI, because we get a lot of requests from you how to analyze electronic dashboards, how to analyze multimedia features, and so on. And Lukas, how do we start if we want to analyze this HMI with ecu.test?
Okay. So first of all, it starts with accessing the system under test, getting a picture from the HMI. Therefore, we need a test bench configuration. I've got one prepared here with our multimedia tool and with an image port in here. On the image port, I can configure how to access the image. So there are different image sources. I can access local pictures. I can access web streams. I can access webcams and application windows on this PC. In this demonstration, we're going to use a local file as a source for our image. Beside the test bench configuration, we need a test configuration. In the media access tab in the test configuration, we create a camera node and assign our image port. Additionally, we provide an image directory which contains our reference images, so the expectations for our testing. And we can add OCR data, so languages that we want to recognize with the text recognition feature.
And do we have more OCR data than English and German?
Yes, so with ecu.test we provide Chinese, German, English, French, Japanese, and Korean language data, but these can also be extended by yourself by downloading them from the web or creating your own models.
Okay, and so now you have the configurations, but how do you actually implement the tests for testing infotainment?
Right after starting the configurations, we have a new tab in our Actions window up here, which is called Media Access. And in here we find our camera and an image node below. And this image node can be read. So if I select to read the image, an image read test step opens up. And in here we can read the image and evaluate the result. On top, we get a preview of the currently read image, which we can also have a look at in full resolution. So this is what we are reading currently. And down below, here in the evaluation, I can select which reference image I want to check for. For example, in here, I want to check whether this media element is visible on the picture. By default, equal is selected, but as media is only a part of the overall infotainment screen, we want to check for it to be contained. I can press OK and have my first reading test step checking for the existence of this image.
Okay, nice. Before you maybe execute it to show the results, can we analyze for text as well? Because we have seen that we can set up OCR data.
Yeah, this is basically the same workflow. We enter the retest step, select an evaluation, but instead of image, we select the string expectation and enter, for this example, media as the text that we want to recognize. Press OK, test step is ready, and now we can execute the test case. Okay, so the image recognition was successful, so we can see this was our expected image. This is the image that we were reading. In the text case, it failed. So we recognized a whole lot of text on this image, so phone, media, vehicle, and so on, and we checked only for media. But by error, I selected equals and not contains once again. So we have to change this, check for it to be contained, to have media within the image, not as the only text in there, and now the check is successful.
Okay, cool. But what if we want to check if the media property in this example is shown at the correct spot? Because now it can be somewhere in my image and it works. Yep. And if I want to check that it's positioned correctly in my HMI? Can I do this as well?
It's also possible. It's pretty similar. So here in the Media Access tab in the Actions window, we have the image node that we used beforehand. And down below, in this example, we have so-called masks. So we defined regions of the image as significant and gave them a name. For example, here, the media mask, I can edit this mask, and we can now see this is the overall image, and we selected this segment of the image to be the significant one that we want to access using this mask. As I did with the image, I can now just right-click and read this media element. And in the test step, I see where the media element is located, once again, is a preview. And I can provide evaluation. For example, once again, I can select to check whether media is part of it. And this time, I would select equal because it's the same extent of the image that I want to check where I provided the expectation. Let's see how this works out. Once again, we see the image we expected. We see the image we read. And down below, we see the overall image, so the whole screen that was read and from which the portion was taken that was compared.
OK, nice. Now, I know a lot of you, they are having not so ideal situations. So, Lukas, can you show us whether we can also analyze it if we have some noise in the picture or we have different color schemes or something like this?
So as new infotainment systems are quite flexible according to their visualizations, you can also make your test step a little bit more forgiving according changes. So once again, I'm going to read the media. I'm reading the same thing, but now imagine we have another reference image. So in this case, it was another theme of our infotainment. So the accent color is green instead of orange. And now this comparison would definitely fail because we're just comparing pixels. What I can do now is just to allow a color tolerance for each individual pixel. And I can also allow a percentage of pixels to be different between the expected image and the actual image. For example, like this. And if I now execute it, then ecu.test tells us that these two images are equal according to the constraints that I provided.
OK, Lukas, but if we now have 10% tolerance, say we have a different text here, we could detect 10% tolerance to different text and still have found correctly, but with the wrong text. So do we have any means of doing special detections of differences? Like not just having 10% pixel tolerance?
Yep. You're right, this is a very general approach. So we just say 10% of the pixels might be different, might be any sort of difference. If we want to specify that only this accent color should be different and should be tolerated, we have to go a little more into detail. Therefore, I would first of all remove the tolerance we just specified, and then I add a filter. So these are pre-processing filters for the images. These are provided with ecu.test, but they can obviously and of course extended by you, so you can add your own filters to it. For our use case here, we can use the HSV filter, as this one allows us to remove the saturation, the color saturation from the image. So now we have a grayscale picture that we read, and also our expectation is grayscaled. So these are comparable once again. And if we now execute the test case, these should once again be recognized as being equal. So also in the report, we see the grayscale versions, which are now the same.
OK, nice. I know that a lot of you have to check for consistency. So as far as I understand you, Lukas, when we do each image retest step here, we always read a new image from the camera. Exactly. So if we want to check if we have, let's say, 2 or 3 features on one image, can we do this as well?
Yes. So this cannot be done in the image read step itself, so it can only check one feature at a time, but we can use the image read step to just read and save an image. That's called the variable screen. So now we just store the image we read at one point in time for later use in this variable, and we can now use the calculation step that you are all familiar with to perform checks on it. So we just access the screen variable and add an evaluation of type image, which is basically the same thing as the retest step can do, the image retest step can do. And we can select our reference image, for example, once again, our media image. And in this case, it would be useful to select contains, so it's just a part of the image that we are checking. This combination would be basically the same as one image read step. So if you want to do multiple checks, you can just duplicate the calculation step and change the expectation, for example, to check whether this phone element is also part of the image. Upon execution, we read once, store the image, and perform 2 checks on it, and can also see that media was found in here, as well as phone was also found in here.
Okay. And speaking of consistency and checking something at one point in time, I know that a lot of users, they have to use or they have to check strict timing constraints, so startup times of HMI or switching times between different screens, which leads us, I think, to the trace analysis. So up to now, we have been to the test case. Can we do all of those features also in the trace analysis?
Yes, so we can do a lot of things also in the trace analysis. But first of all, we have to record the video feed, the video signal. I prepared this one for the demo, so we can just read the image node from the media access tab, put it into here. And in this case, for the demo, I also prepared a video and just referenced it in here. But you can also read while executing the test case, of course. This video contains a boot up sequence, so first a black picture and then the infotainment screen is visible. This signal can be added to a trace analysis also, like so. And now we can create our trace steps to access the individual images in the video stream, in the signal, to perform checks on them. Therefore, we also provide a set of specific trace step templates. For example, one to calculate the brightness of the image, to check for black screens, or to check whether the boot sequence is finished. We have a trace step template for finding images, checking whether image is visible.
Which is quite similar to the test case, just in the trace analysis.
Yeah, we're about to use this one. But there's also one which can speed up your checks tremendously, which we want to use first, which is reduce video. So the resolutions of the videos are quite high, the frame rates are high, so the quality is very good, but this has negative impact on the performance of the checks, because the checks are all performed for each and every image. So for our example here, we first of all want to reduce the frame rate of the video. So our source video has 25 frames per second, but we just want to check whether the image, the media element, is ever visible in the video. So if the boot sequence is ever finished. Therefore, it's okay if we just check 10 frames per second and just skip 15 of them to improve the performance. We could also downscale the video, which we do not want to do in this case. And we could also convert the video feed to grayscale, which would also benefit the performance and would also help with tolerating the color schemes we had beforehand. As an input signal, we select the camera image, so the video feed, and we create a new output signal. Let's call it output frames. Now, after this step, we have our reduced video, and this can be used in the find image trace step as an input signal. And in here we can, as we did before, provide an image that we expect to be in here, that we want to check to be in here. Let's once again select our media picture. We could apply a mask, but we'll not do this right now. And we can provide a threshold. So once again, adding or removing tolerance to the comparison. In the trace analysis, it's quite necessary to apply a little bit of tolerance, because video compression is more aggressive than picture compression usually, and therefore you will have some artifacts, for example, in the video images, and you have to cope with them. Therefore, you will not have a perfect match usually. I will go to 59% correctness, so 5% of tolerance in the image. The find image trace step template does not return a success or failed. It would just emit another new signal which contains true or false values depending on if the image was found at a certain point in time or not. So
and then we can just use this scalar signal to use our normal checks and calculations, and every check we can do with the trace analysis. Could be a perfect trigger signal for a trigger block, for example. Yeah.
Okay. So now we have this new signal contains image which has values for each and every point in time, whether the image was visible or was not visible. And now we can finally add a calculation step, as we know how to use it. Check the signal contains image, and check whether check that it is fulfilled at least once during the whole trace analysis.
So that our boot sequence actually finishes and shows our HMI in the end.
Yeah. So it's a very, very basic check test here. We just want to find out if it is ever visible. Now we can execute. And as you can see, it still takes a little bit of time. Video analysis is way more complex than static image analysis. There it's done. We can have a look at the analysis. We already see it's successful. And we can see in the calculation that for 7 seconds the image was not visible, but for the last 3 seconds it was visible. And to have a bit deeper look inside, we can open it in the AutoSpy viewer, see that the contains image initially is 0 and later on switches to 1. And we can also add in here our video feed, our output frames, which is the reduced video. And in here we can see each individual frame of the video and zoom in here and see the switch. So before this image, of course, media is not visible until this point. Here it is visible, and therefore success started at this point.
Okay, very nice. And especially that in the AutoSpy viewer you see not only the contains image signal with changes from 0 to 1, but the output frames as well, so you can really check later on that everything is right. Yeah. Okay, so now we did in the test case and we did in the trace analysis checks for different images and texts and so on. But if we want to stimulate our device under test, so for example, press a button or something like this and navigate through a menu, can we also detect, let's say, the position of an image? So not use a mask to detect if it's at a position, but detect a position. Especially important with nowadays HMIs where you can change everything. Do we have some possibilities there as well?
Yeah, this is also possible, but not with the ready-to-use test steps, but with our API. So it's really advised to have a look at our APIs because they're more powerful than what we can provide in a convenient test step at this point in time. I'll show you an example. Get rid of these. We already stored an image here as screen, and now we can use this image and perform additional checks on it. Also with the calculation step. And for example, on this screen variable, we can check whether there is a certain text available on there and get its position. This is quite easy to do with the function find text. And we can just provide text. For example, here I want to check if ON is anywhere on the screen. And if I run this one, the API call, the find text, returns a match list, so-called match list, which contains all the matches. So in here, it found 2 strings which contain ON. One is phone, one is app connect, and it also provides the position of these text elements and their dimensions. We also get a preview in here, so phone was located and app connect was located, because both of these contain ON.
Okay, and now I can use the position or dimension I get from there and, for example, stimulate my HMI to get to the next interface.
Yeah, so this is one possibility. If you know what you're searching for, you can find out where it is. This is also possible with images, which is a little bit more complicated. Because of that, I will skip it right now. Another approach for text, in particular, would be to say, I just want to know what is displayed to find out where I am currently, for example, for orientation in the test case. I can just say, I do not expect any text. I just want to get all text that's displayed currently. I just have to provide a threshold here to eliminate, let's say, false positives, so misinterpretation of symbols on screen as text. For example, a circle might be interpreted as an O, or some symbol might be an @ or copyright symbol. This happens quite often.
Okay, might be especially useful for our international customers when you have some non-Arabic characters interpreted as text. It's probably not so useful.
Yeah. Now we can see here that all the different text elements in here were recognized. The text is in the match objects as well as their position. And now I could use these positions to locate the icons above and check them for some content, or to perform an action on these. For example, sending a bus signal to perform an activation, a tap on it, for example.
Okay. Well, very nice. Then thanks, Lukas, for the introduction on the multimedia features. I hope you guys got a good impression on what's currently possible with ecu.test, and see you probably in the next video. Bye-bye.
Bye.
Viel Erfolg, Jungs.
Danke. Willst du mich verarschen? Du hast zwischendurch noch tauschen oder was?
Feature Tag. Ich weiß nicht. Ich will mal kurz ausmachen. Ich würde das kurz einmal ohne Video machen.
Das Video ist aus.
Nee, das Video ist die ganze Zeit an, weil ich weiß nicht.
Da waren. Entschuldige, nochmal bitte.
Bist du ganz sicher?
Ich bin mir ziemlich ganz sicher.
Sehr gut.
Now you can clap, Lukas. Please.
Yeah!
Ja.
Scheiße.
Das machen wir nochmal.
Nee, weiß nicht, wie das aussieht.
Also außer, er fährt nicht runter, sondern er fährt bloß in den...
Das ist ein Standby gegangen, glaube ich.